Welcome. In this video, we are going to find a formula for the first derivative of this function, that is f of x equals the square root of x, using the limit definition of the derivative. So remember, that is, recall, the derivative can be found by evaluating the limit as h approaches 0 of f of x plus h minus f of x, this entire quantity then divided by h. So this is the limit as h approaches 0 of the square root of x plus h minus the square root of x divided by h. And so all I've done here is, using function notation, taken whatever is inside, in this case x plus h, and put it inside the square root function. Now this is going to require a little bit more algebraic manipulation than we have done up to this point with these limits. So let's go ahead and multiply the top and the bottom by the conjugate, that is the root of x plus h, plus the square root of x. And again, we're doing that to both the numerator and the denominator. So this is the limit as h approaches 0. And instead of multiplying this out the long way, remember a difference of squares. That is a minus b times a plus b. That's equal to a squared minus b squared. And that's precisely what we have here. This is our a minus b here. So the result is the square root of x plus h quantity squared minus the square root of x squared divided by, and here I'm going to warn you, don't try to multiply this out, and you'll see why in a second. So this is h times the square root of x plus h plus the square root of x. All right, so we have the limit as h approaches 0 of x plus h minus x divided by h times the square root of x plus h plus the square root of x. All right, as you can see, we have a positive x and a negative x. Those add to 0. So we're left with the limit as h approaches 0 of h divided by h times the square root of x plus h plus the square root of x. Now, I think you can see why I suggested you not simplify the denominator here, because it makes it very clear that this h and this h, well, h divided by h is 1. So we can rewrite this as the limit as h approaches 0 of 1 over the square root of x plus h plus the square root of x. All right, let's go ahead and finish this up. So I can go ahead and plug in the 0 for h, and it will not impact this function. That means, or this expression, that means the 0 does lie in the domain of that expression. So I can drop my limit notation finally. This is 1 over the square root of x plus 0 plus the square root of x, and this equals 1 over 2 root x. Okay, so f prime of x is equal to 1 over 2 root x. And now let's chat about the domain of both of these. Since wherever our original function is not defined, our derivative cannot be defined. All right, I made a little extra space here. So the derivative, not the derivative, the domain of f is just x greater than or equal to 0. So then what does that tell us about the domain of f prime? Well, the domain of f prime of x certainly has to be greater than 0. What about equal to 0? And I'm going to put this as a dotted line here with a question mark. What about equal? Can this function equal 0? If you answered no, you're correct. It cannot, because that would yield a 0 in the denominator. So let's take a look at this graphically, and I'm going to just give you a rough sketch of both of these to get an idea of what's happening. Here's x, here's y, and let's go ahead and change the derivative to green so we can tell these apart. So our original function is like this. This is y equals f of x. Well, what is going on near the origin? Well, clearly the slope of this curve is pretty steep here, and it becomes less and less steep. In fact, it's becoming almost completely flat as this function goes out to infinity. It's never going to be completely flat. So that tells me this very steep line has to be a very high value for the derivative, and this less steep line has to be a low value. So my derivative function is going to look something like that. So I know the derivative function will look something like this. But what happens as we get closer to the origin? Well, let's take a look. This tangent line is steeper than this one. This tangent line would be steeper than this one. In fact, as we get close to the origin here, we're approaching a vertical tangent line. That means the tangent has to have a vertical asymptote here. There we are. This is y equals f prime of x. So again, the slope of the tangent line here is not very steep, so the derivative function has an output that's close to the x-axis. The derivative here of the function is more steep, so that means the output of the derivative function has to be higher up along the x-axis, and it's a larger output. And as we get closer and closer to the origin, the slope gets steeper and steeper, so the derivative function is blowing up here towards the origin. Hopefully you have gleaned not only enlightenment from this little video, but also a touch of pleasantness and entertainment.